Magnets are pretty much everywhere. They're in your headphones, the phone in your pocket, holding stuff up on your fridge. Heck, our entire planet is one giant magnet. But even though we see them every day, there's still something kind of magical about them, isn't there? This invisible force that can push and pull with some serious strength.
So what's really going on here? What is it that makes a simple chunk of metal magnetic? Well, in this explainer, we're going to pull back the curtain on this invisible force. We're going to take a journey from the things we see every day right down into the bizarre world of quantum mechanics.
All right, let's dive in. First, we'll look at the magnetic fields we can actually see in action. Then, we're going to zoom way, way inside a magnet. From there, we go even deeper to the quantum level, which is where things get really wild. And finally, we'll zoom back out to see how this incredible force shapes our world and what the future holds for it. Okay, so first things first. Let's talk about the part of magnetism we can actually interact with, even if we can't see the force itself, the magnetic field. So a magnetic field is basically this invisible bubble of influence around a magnet where its power can be felt. You can't see it with your own eyes, but you can definitely see what it does. I mean, if you've ever sprinkled iron filings around a magnet, you've seen it. You see how they magically trace these invisible lines of force, mapping out the field's shape right in front of you. This field is a product of electromagnetism, and that's one of the 4 fundamental forces of nature, right up there with gravity. It's a big deal. Now, the number one rule of magnetism is super simple. Opposites attract and likes repel. A north pole will always pull toward a south pole, but try to push 2 north poles together or 2 south poles, they'll fight you every step of the way. This force is strongest right at the poles, and it never really goes away. It just gets weaker the farther out you go. So that's the basic behavior, but it raises a much bigger question. What is happening inside the magnet to create these poles in the first place? To answer that, we have to zoom in. Way, way in. Because the secret isn't on the surface. It's woven deep into the atomic fabric of the material itself. Okay, so here's the breakdown. Every single electron zooming around an atom creates its own tiny little magnetic field. Now, in most stuff, these fields are all pointing in random directions, so they just cancel each other out. But in special materials like iron, something amazing happens. Groups of atoms get together and line up their magnetic fields, forming these little neighborhoods called magnetic domains. At first, all these domains are still jumbled up, but if you bring a strong magnet nearby, they all suddenly snap into alignment, all pointing the same way. And when all those trillions of tiny magnetic forces add up, bam, you get one powerful magnet that you can actually pick up and use. But see, that just raises another question, doesn't it? Why? Why do these electrons decide to line up in the first place? Well, to get that answer, we have to go even deeper into the strange and wonderful world of quantum mechanics. Okay, the true source of all this is a quantum property called spin. And I have to be clear here, the electron isn't literally spinning like a tiny planet. It's just a fundamental built-in property it has, like its negative charge. The best way to think about it is that every single electron is born with its own tiny permanent bar magnet attached to it. It's just part of what an electron is. And because it's a charged particle, that spin generates a magnetic field. So if every electron is a tiny magnet, why isn't everything magnetic? Great question. It comes down to a fundamental quantum rule called the Pauli exclusion principle. It basically says that 2 electrons can't be in the exact same state in the same spot. So in an atom, when 2 electrons have to share a space, one will have its spin up and the other must have its spin down. Their tiny magnetic fields point in opposite directions, and they cancel each other out perfectly. And that's why most materials just aren't magnetic. So what makes things like iron, nickel, and cobalt so special? It's all because of a bizarre effect called the exchange interaction. In these particular materials, it's actually more energetically stable. It takes less energy for electrons in neighboring atoms to align their spins in the same direction. This quantum need to line up is so powerful, it completely overrules their tendency to pair up and cancel out. This right here is the secret sauce. It's the deep quantum reason that those magnetic domains we talked about can even exist. Okay, so we know how the fields are created, but how do they actually talk to each other across empty space? Well, this is where it gets even weirder. The force is actually carried by tiny messenger particles called virtual photons. Think of it like this. Imagine 2 people on boats. If they start throwing a heavy ball back and forth to each other, what happens? They push each other apart. That's repulsion. But what if one throws a boomerang that swings around and is caught by the other person from behind? It would pull them closer together. That's attraction.
Virtual photons are those invisible balls and boomerangs, constantly communicating the push and pull of the magnetic force. So what this all boils down to is that the very real push and pull we feel from a magnet is really the result of this deep, invisible quantum dance. It's all about the probability of where electrons are and how their fundamental properties interact with each other. It's a mind-bending reality for sure, but it's the engine behind one of the most powerful forces we know. Okay, so let's pull back from all that quantum weirdness. Now that we have some idea of what's going on, we can really appreciate how we've harnessed this invisible force to literally build our modern world. In the impact of magnetism on our lives, it's massive. It's the magic behind how we store trillions of gigabytes of data on hard drives. In hospitals, powerful MRI machines use magnetism to see inside the human body without a single cut. It's the fundamental principle behind every single electric motor and every generator that powers our homes. And on a planetary scale, the Earth's own magnetic field acts as a giant shield, protecting all life from dangerous radiation from the sun. Let's just take a hard drive, for instance. A tiny right head creates a very precise magnetic field. This field flips the quantum spin of electrons in a tiny spot on the disk to represent a 0 or a 1. Then a read head comes along and detects which way those spins are pointing to read the data back. And the whole thing works because the material has a memory. It holds on to that magnetic information. So every photo, every file, every bit of your digital life exists because we learned how to control that little quantum dance of electron spin. We've done some incredible things with magnetism, but believe it or not, we're really just getting started. We're constantly finding new and amazing ways to put this force to work. I mean, today we're building absolutely colossal superconducting magnets to smash particles together at nearly the speed of light, trying to unlock the deepest secrets of the universe. We're using magnetism to lift entire trains off their tracks so they can float through the air for ridiculously fast and efficient travel. We're even developing ways to use magnetic nanoparticles to deliver medicine directly to cancer cells and destroy them from the inside out. The future really is magnetic. So from the quantum spin of a single invisible electron to the massive protective shield of our entire planet, magnetism is this fundamental force that's both incredibly mysterious and profoundly useful. It's a perfect reminder that sometimes the most powerful forces in the universe are the ones we can't see at all, silently holding our world and all of our technology together.